Good morning, everyone. Myself, Vishwas, Chair of the IEEE Computer Society, Bangalore chapter, along with Anand, our Secretary. We are very pleased to host this webinar today. And in the next 1 hour, um, we'll first begin with the introduction to our chapter, followed by the talk by the speaker today. And you can always post your questions in the chat box on WebEx. And most relevant questions will be taken up by the speaker and answered at the end of the session. This is part of the Celebrating Computing webinar series from IEEE Computer Society, Bangalore chapter. We've been hosting many webinars since last couple of weeks. This is the third one in the series, and it will be AdaSwarm, a novel PSO optimization method for the mathematical equivalence of error gradients. And we are very glad to have Professor Snehanshu Saha from BITS Goa as a speaker today. A warm welcome to you, Snehanshu.
Thank you.
And to introduce Dr. Saha, he is currently Associate Professor of Computer Science and also the member of the Center for Artificial Intelligence Research at BITS Pilani, Goa campus. He holds a PhD in applied mathematics from University of Texas in Arlington, and also MS from Clemson University in applied mathematics and computational sciences. Until recently, he was with PS University, Bangalore, until December last year, and then he moved to BITS Pilani Goa campus. He was also the chair of the Computer Society Bangalore chapter until the end of 2019. He's an accomplished academician and researcher in the field of machine learning, data science, and astronomy. And he has more than 90 peer-reviewed publications to his credit. And he also is a fellow of IEEE and a senior member of IEEE and a senior member of ACM. Without much ado, I will hand over the virtual stage to Snehanshu to begin his talk. And before that, I just want to tell the participants that you can be in touch with us anytime through our website or email us through this email address. And also, we are very active on Instagram, Twitter, Facebook, and LinkedIn. Please do follow us. We do have a lot of events coming up. Even in June and July, we'll have a lot of webinars, especially in this COVID 19 times. Otherwise, we would have a lot of face-to-face events, but now we are forced to go virtual, and we are happy to bring them to you. Almost every week we have a webinar, so please do follow us on any of these social media channels, and we'll be glad to connect with you and also keep you updated about our events. And post the event, a feedback form will be sent. Please do fill that out. It will really help us in organizing the next set of events. And now I hand over the virtual stage to Dr. Saha for his talk on AdaSwarm. Thank you.
Dr. Saha, before we begin, all participants kindly mute your mic and disable your video. You can post the questions in the chat window and it will be picked up by the speaker and answered towards the end of the session in the Q&A session. Thanks a lot for joining us. Over to you, Dr. Saha.
Thank you, Anand. Thanks very much. I'm very pleased to be here today and talk about some of the things that I actually didn't believe in when I began this journey. But as time progressed, I started to see some insights into the methods that I'm going to talk about today. Am I on the presenter mode, Anand?
Yes, you are.
Okay. All right. Okay. So I'll just start with my slides. Okay. All right. So the title says something. and we will talk about what the title is. Vishwas has already given a very kind introduction to me, so I wouldn't spend much time except just mention the fact that some of the talks in this webinar series are jointly conducted between IEEE Computer Society Bangalore chapter and the Anuradha and Prashant Palakurti Center for Artificial Intelligence, Pittsburgh campus.
Dr. Saha, have you started sharing?
I think so. Hang on. Haven't I?
Not yet. Not
okay,
yet.
Not visible yet.
Yeah.
Share content, is it? Oh, okay. All right. Is it visible now?
Yeah. Yeah.
All right, great. And so I think just so that there is some issue with the internet here, so I'm just going to what I'll do is I'm just going to mute my video.
Again, the presentation actually went.
Hang on. Because I was trying to get to my video. Oops.
The second button from the left, you just have to disable it.
Yeah. Okay, I'll just disable the video and I'll just share the content. So the share the content is which button, Anand? Okay, got it.
Third button, yeah.
All right. So is the presentation visible?
Yes.
Okay. All right. Thanks. Yeah. Sorry for the confusion. So the talk is delivered is a joint. Some talks in this series are a collaborative effort between IEEE Computer Society Bangalore chapter and the Center for Artificial Intelligence at Pittsburgh. Okay. The title suggests that we will be talking about some sort of a swarm optimization method, and it's kind of adaptive in nature, as I explained later in the later part. But where it started from is just a very simple yet powerful algorithm called particle swarm optimization. Okay. Now, when I started this journey some couple of years back, I mean, the landscape was something different. I wanted to solve some optimization problems in astronomy, and that was the goal at that point of time. Okay, but as I discovered when we went through the nitty-gritties of the method, that it's sort of a lot of it is actually black box, as you will discover today. Okay, and then there is these set of black box methods powered by neural networks as well, right? And my personal preference, as some of my students know, that I don't like black boxes. Okay, so the question is, what am I doing with two black box methods? One is particle swarm optimization, and the other one is neural networks and deep learning. The short answer is, and I will give you a long answer. The short answer is, what I have tried, particularly in the last 6 months, and the talk is actually as a result of this, is to see some insights from both of these methods and try to connect. So as you will see, while modifying the existing particle swarm optimization method, I have borrowed some ideas from the neural network, and then later I used this improved particle swarm optimization method to give back to neural networks. Okay, so that's the broad overview. And in the process, while trying to discover some insights, we ended up proving some important results that I will also discuss. Okay, so I'm sure you have seen a flock of birds moving in a certain direction, right? And a school of fish and some other things, right? So it's sort of a colony optimization method where certain animals move in, I wouldn't say predefined, but they do move in a sort of a shape, and that shape changes. But you must have noticed when you watched migratory birds flocking from one place to another place, they tend to keep a very closely knit colony, which means that there are individual birds that are flying, right? I mean, I don't think any bird is helping another bird in the colony to fly. Each bird is flying on its own, but they're flying in such a manner that the group stays close to each other. Okay, so this kind of grouping behavior or herding behavior is modeled by using several meta-heuristic algorithms, and colony optimization being one. Okay, there are some leapfrog algorithms, wolf colony optimization, and particle swarm optimization. Okay, interestingly enough, even though this is used in computer science a lot, this method was originally discovered jointly by a social scientist, okay, and an electrical engineer back in 1995, right? So these are the two guys, Eberhart and James Kennedy. And so the original idea came from Kennedy, where he was thinking, I mean, how do we use sort of a grouping behavior and use individual contributions to a group to improve the overall group dynamics? Okay, like he was studying some group performance and things like that in the classroom. And then Eberhart came in, and he's an electrical engineer, and then he actually proposed the model. So some of the slides are actually adapted from their presentation and a presentation by Maurice Clark, who is himself a pioneer in particle swarm optimization research. Okay, but let's talk about Sharmaji ki beti first. All right, I mean, for those who don't understand Hindi, this is about a very popular, sort of, you can use it as an inspiration, you can use it as degradation. So Mr. Sharma's daughter. All right. Now, I mean, we all grow up in neighborhoods, right? I mean, even though these days we live in apartment complexes, but at least when I was growing up, there are a lot of, social interactions among the neighbors. There are, of course, good things, and then there are bad things depending on how you look at it, right? So I don't know how many of you grew up, hearing this. I grew up listening to this. Oh, look at that boy. Or look at that girl, see how well she is doing. What are you doing? This is typically a jibe from the parents, right? I mean, I don't think the intention is bad. So what they're trying to do, they're trying to push you towards emulating some of the best things that probably your neighbor's son or daughter is doing. Okay. So in a neighborhood, somebody is a role model, let's say, right? And you try to emulate the behavior and some of the performance of the role model. Okay, I mean, if you're a positive guy, right? I mean, if you think of this as sort of derogatory towards your own existence, you could completely shy away from that person and even start hating that person, right? Okay, but I am assuming that we are all sort of mature individuals, and so we try to learn from each other. Okay, and we try to learn from experts in the field, right? So this Sharmaji ki beti, or Sharmaji's, I mean, Mr. Sharma's daughter, is sort of someone who we try to emulate. Okay, so in particle swarm optimization, there is something known as a globally best solution. Okay, so we'll think of Sharmaji's beti as a globally best solution that you try to reach. All right, and you have your individual best, or you have some random performance that you probably have done, right, without much effort or whatever. Okay, so the idea is going from an individual, how one individual or a bunch of individuals in cooperation with each other learn to improve their own performance, okay, towards a goal, and try to reach a globally best solution. Okay, all right. So this is the binding principle of a particle swarm optimization method. Okay, it's a simple but powerful philosophy. I mean, if you really think about it, right? And where I come from, I have to give this example. Okay, so where I come from, fish is a staple food, and so Bengalis love fishing. Bengalis love to eat fish, right? So those who have some experience in fishing know that it's not an easy job, right? So the idea is, suppose there is a bottom feeder. Some fishes are bottom feeders. They typically stay at the very bottom of the pond or a lake, right? Okay. And what two friends are trying to do they are trying to measure the depth of the lake. Okay. All right. And they actually have, no idea over the overall depth of the lake, right? And so they have to explore. So when you start exploring, it's sort of an individual exploration. Okay, so let's see. These are the two friends. Okay, and this is an example of cooperation. As I said, I mean, if you take things in the positive spirit, okay, you tend to cooperate with each other. So how do you cooperate? You cooperate by giving a shout out to your friend, telling the other person what? You tell the other person, look, I'm here in this portion. Okay, this is my depth. What is your depth? Then the other guy says, oh, your depth is 3 meters. I think what I measured is 3.5, right? And then the guy who has measured depth of 3 meter, she or he needs to move towards the direction of the other person, because the goal is to get to the bottom of the lake, or goal is to get to the best possible position, right? So what are we doing here? We are actually, in terms of computer science language, we are actually trying to solve a search problem. This is a search problem. What is your search space? Your search space is an irregular surface. You can see that, right? I mean, sort of jagged. I could have made it more jagged, but you get the idea, right? If you also look at the shape of the surface, you probably also have noticed that you go down and then suddenly there is some upward trend, right? So it's not like something like a soup bowl. In a soup bowl, what happens is you start from the top of the bowl, and if you let a ball roll, it will roll down, right? It will probably have some oscillations, but eventually it will settle down at the bottom, okay, after some iterations. Why does it do that? It's because there is just one bottom, and irrespective of whichever way you look at, right, the only way is a smooth way down. So you can think of that surface as a smooth surface, and searching for a global minima or a local minima, or searching for a minimum point in that surface is sort of an easy problem. Okay, but surfaces like this have their own challenges. I mean, you could have a bunch of ups and downs, and then you just keep on searching, and you probably think that this is my best, but I mean, this is the best, or this is the maximum depth that I could have attained. Like, for example, if I go towards each other, right? And so this searching process continues. So there is a chance that you could actually get stuck in sort of a local minimum. What is a local minima? A local minima is a point where you think you have reached the minima of that surface when you are searching, but it is actually not the minima. There is a further depth, as this illustrative example explains to you. So what do? You keep going. You keep going, you keep communicating, right? And please notice the position of the fish, right? And we have to keep doing this, right? So the other guy, the guy in green, realizes that she is not actually in the best position, because she is continuously communicating with her friend, right? Okay, and so therefore, since she is not in her personal best position, or rather her personal best position is actually not the global best, what is she supposed to do? She will move towards the global best. In this case, she actually doesn't know what the global best is. So she will rely on her partner, and if her partner's position is better than hers, what she will do is she will continuously move towards the position of her partner. Okay, all right. And this is how the search is accomplished. And eventually, and this communication process goes on and on and on until both of them sort of decide or agree that they are in a position which is at the maximum depth of the. Okay, all right. So this is a search problem, but what are you searching for? You are searching for the optimization. You are searching for a point which is optimum. In this case, the maximum depth of the lake, or the lowest point in the lake, right? Okay, so think about this. If you have some function, okay, you use that function and use some techniques whether classical techniques or the kind of technique that I'm talking about. Now, your objective is to find the global optimal point of that particular function. Okay, all right. This optima could be a minima, it could be a maxima, depending on the problem. But if you are able to solve the minima problem, solving the maxima problem is just easy. It's just the counterpart of it. Okay, all right. So having said that, so let's move to the basic tenets of a swarm optimization. So as I said, each particle is searching for the optima, but while doing that, each particle has to move, right? I mean, they could also move without caring for what the other guy is doing. Like, for example, if I go to that Sharmaji ki beti example, right? I could have told my parents, I don't really care about Sharmaji's beti. I'll do what I think is best for me. That is also fine, right? But so sort of in search for, doing better and better and better, right? I need to have some velocity. So what happens in a swarm, whether it's a swarm of birds, whether it's a swarm of fish or something, each member of the swarm is considered a particle. Okay, so each particle searches for the optimum, and each particle therefore needs to move in the search space, move around in the search space. Since it's moving around in the search space, it must have a velocity, right? And it's a velocity vector. Also, there is some memory. Okay, there is some memory because the particle should remember where it was before. Okay, because it has to compare. So there comes the iterative process. Okay, because if a particle moves to a certain position where it was actually doing worse than what it was doing in the previous iteration, then it is not the particle's personal best, right? Okay, so, but as you can see, in the absence of a cooperative environment, if it's just one particle, it can do as much as it can. I mean, there is a limit, right? So therefore, the cooperative environment needs to kick in. All right. So they need to cooperate. How do they cooperate? There needs to be other particles in the swarm. And as I gave that particular example, a particle has a neighborhood associated with it. And in this neighborhood, the particle does a local search. Okay. All right. And since the particles are communicating with each other, each particle knows what is the best of the fellow particle or the neighborhood particle, right? And this is known as the fitness. So in any objective function optimization problem, right, the fitness is a key. So you tend to improve the fitness of the neighborhood, and thereby using that fitness, change your position to a more favorable position. Okay, you keep on improving the fitness until you reach a point where you can't improve the fitness any further, right? And you can set that limit by setting a limit on the maximum number of iterations and so on and so forth, right? And then you stop the algorithm. Okay, so what do you do with the position? See, you are in some position and then you move to another position, right? The position is simply used to adjust the particle's velocity. Okay, all right. So here is a landscape. So as you can see, there is a geographical landscape, right? And so there are some positions and velocities which are arbitrarily assigned, right? Okay. And then, of course, each particle will have some neighborhood which it should communicate in between, right? And remember, this is a surface where you can see there are like the surface is flat in some positions, it is curved in some other positions, and then there are some peaks. Interestingly enough, I mean, if you notice carefully, there are at least 2 peaks, and these are sort of hard optimization problems. Okay, all right. So you need to have a global search as well as a local search. And since you are actually on the periphery, you are more on the flatter part of the plane, right? You need to move towards the peaks by cooperating with each other. So it is sort of like a hill climbing problem. Okay, all right. So as you can see, there are directions. These directions could be random, right? I mean, it's sort of a randomized search algorithm, but like any randomized search algorithm, I mean, the convergence is always an issue, right? So there has to be, I mean, in the absence of a model, you can continue doing a search this way and you may reach the optima, right? But it may take a lot of time. right? So let's now talk about a model. So model in terms of a particle. So as we said so far, that each particle has a position, each particle has a velocity, right? And then the position needs to be adjusted because you need to move towards your personal best as well as a global best, right? Okay. So how are you going to do this? I mean, I'll skip this slide for now, and I'll also skip these slides for now. I'll just move straight away to this, okay, and I'll come back to the previous 3 slides. Okay, so you can see this, right? I mean, you can see that there is initial position of a particle, and that's where I am. I mean, if I'm a particle, that's where I am, right? And I know what my personal best performance is, right? And there is also a global best performance of my neighbors in some other position, right? Okay, and I can move with a velocity vector in a direction, in certain direction, right? All right, what is the goal? The goal is, see, I am comfortable with doing something, right? But then once again, this society thing comes in play, right? Okay, this Sharma ji ki beti thing comes into play. Oh, this girl is doing so well. What are you doing? So the peer pressure helps you, improve your own performance. Whether you want to do it on your own or whether you are forced to do it doesn't really matter. But in the end, what matters is your performance is improved, right? Which is why parents always want their kid to be placed in a good academic institution, because what happens in a good academic institution, that you have a bunch of guys, you have a very good ecosystem where you have a bunch of other guys who are doing very, very well. My advisor actually told me some time back when I was finishing up my PhD. He said that, look, don't play squash with a guy who is worse than you. So what will happen is you will get better and you will become worse. Get the point, right? Okay. So if I extrapolate that, I can say that don't join an institution where you are the smartest guy. Okay, it doesn't help you. Okay, so well, back to this. So here I'm in the particle. So I actually, what is my final goal? I actually need to move towards a global best. Now remember, all of these are vectors, right? Okay, so how can I do that? Well, I can move with a particular velocity, right, in a random direction. But as soon as I realize that this is not fetching me my personal best, I need to readjust my position, correct? Right? Okay, how do I do that? I know which direction my personal best is, so I need to move in the direction of that vector. As it stands, what I can do, I can move in a direction parallel to that vector, right? Okay. So this is where my personal best is, and I need to move in that direction, right? So you see a vector directed in parallel to the vector that is towards my personal best. Now remember, from my original initial position to my personal best position, this distance can be easily computed, right? And this distance is nothing but the difference between the personal best and the original position of the individual particle. So it's just the subtraction between pi and x, right? Okay, but remember, I am moving in a direction parallel to the pi minus x. So what I need to do from vector algebra, if you recall, you just need to multiply this pi minus x with a scalar. Okay, remember this. Okay, all right. Now, am I done? No, I'm not done. So what do I need to do? Well, my ultimate goal is to move in the direction of what? In the direction of the global best. So I need to be moving in that direction, right? Okay. So this is my global best, not my global best. This is the best performance of my neighbors. Okay, somebody, right? I mean, Sharma ji ki beti in this example, right? And what I do is I move in that direction. Okay. Once I have ascertained that I have aligned myself with my best neighbor, I'm sort of done. Okay. Plus, also remember, there is one thing. there is this P of G, right? This means the global best. And then there is this initial position X. So you have to move yourself towards the global best. That means once again, you have to traverse some distance. How do you calculate that distance? That distance is once again calculated as a simple difference between PG and X, right? Okay, but once again, since you are moving in a direction parallel to that vector, you need to multiply with some scalar. As it turns out, these scalars are actually very, very significant. These are actually called acceleration coefficients. Okay, how quickly you are converging towards your personal best and how quickly you are converging towards the global best. Okay, so these three components. So how many components do I have now? I have one green arrow, second green arrow, third green arrow. We have three components. These three components together will constitute my relationship between my original position and the global best, right? Okay. And here we are. That is exactly what I just explained. So now we have a model, very, very simple model, very simple to follow, right? So what I do, I have two update rules. I have a particle position update rule and I have a velocity update rule. So how do I update the position? The new position is just the sum, a vector sum of my previous position and the velocity, right? If that works, fine. If it doesn't work, I need to update that velocity. How do I update that velocity? I need to update that velocity with my initial velocity, whatever velocity I started with. And then I have this P best minus P. Let me go back to this image. P best minus P, which is my difference between my personal best and my original position, and G best minus P. This is the difference between the global best and my original position, and each one of them multiplied with two scalars, I mean individually C1 and C2, and these are the weight of the local information and weight of the global information respectively. And they are also called acceleration coefficients. Okay, multiply these two with two random numbers to facilitate your search quickly. Okay, and these random numbers are sampled from a uniform distribution between 0 and 1. Okay, all right. I have presented a very simple scalar form of the two models, but remember, this should be represented in a vector notation, right? And this is, both of these update rules are for individual particles. Okay, the moment you want to have, want to represent a particle as a member of a swarm, which is nothing but a set of candidate solutions for your particle search optimization problem, right? You need to have some index with both P and V. So later on, you will see I will switch to notations like PI and VI. While PI stands for particle I in the swarm, right? Where there are I number of particles, the value of I ranges from 1 to n, and V as VI, where that represents the velocity of the ith particle. Okay, all right. I think so far it should not be hard to follow. Okay, all right. And here we are. That is exactly what I was talking about. This is the indexed notation. And as you might have understood by now, is that since this is an iterative algorithm, we need to keep track of the time step, right? Which is why I have a superscript, okay, which is I update the velocity of a particle at any time step, okay, by utilizing what? By utilizing the previous velocity at a previous time step and the other two factors in my swarm model. Okay, all right. Now let's get some terminologies out of our way. The first term on the right hand side of this is known as inertia. So when Eberhart and she proposed their particle swarm optimization algorithm in 1995, they presented it this way. But what we have done is we have added a scalar coefficient with the velocity, just so that you can sort of randomize the direction of the velocity, right? Okay, and so later you will see that there would be a scalar that is added to this velocity multiplied with this velocity, and it's called an inertia term. Okay, all right. The second term on the right hand side is a personal influence. Okay, and this is and the third term on the right hand side is a social influence, as it is clear for now. So the personal and the social influence combined is the social is fine. The personal is known as a cognitive effect. Okay, so you try to improve your own performance. Okay, irrespective of whatever your neighbor does. Right. However, think about this. If I ignore the second term and the third term completely, what am I doing? I mean, I really don't care about what my neighbor is doing. I really don't care about improving my own performance. I'm a happy-go-lucky guy, and so that you can still apply the particle swarm optimization algorithm, but then what you will have some velocity which doesn't need to be updated, and you can keep on just changing the direction of the velocity vector and keep updating your position and be happy. Okay, so without a cognitive influence or a social influence, you are just as good as you're on your own. Okay. However, that's not the objective though, but I'm just telling you what it could be in the absence of the second factor and the third factor in this model. Okay. All right. Well, I mean, this algorithm is pretty simple to follow. You update the position, you update the velocity, right? And you keep iterating, right, until you find the G best. Okay. All right. Now, there could be several things to consider here. One is that you probably have noticed, if I go back to this slide, that there are a bunch of variables involved. In fact, this original particle swarm optimization model has been modified, and two random numbers, two random coefficients, as I said, sampled from an uniform distribution between 0 and 1 has been added to the second and the third term, and the velocity is also multiplied with another scalar, right? And that is called an inertia coefficient. Okay, so usually people don't know the exact values, and which is why this is known as a meta-heuristic algorithm. I mean, there are some elements of black box, and you keep on trying different values within their ranges until you reach a solution. Okay, all right. Which is why I did not actually used to like this particular method, as I told you in the beginning of my talk. Okay, until I realized that there is more to it than meets the eye, right? So now, therefore, velocity is an important factor. I mean, if you move too fast, what will happen? If you move too slow, what will happen? So in the context of an optimization problem, what it implies is if you move too fast, you could be actually, you actually could shoot off your local minima, global minima, or global maximum. You just tend to, I mean, you are just a loose cannon, right? Who just likes to move around with really fast with no sense of direction or purpose, right? You could shoot off. If the velocity is too low, what will happen? That you may reach the global optima, or like a global maxima or global minima, but it will be painstakingly slow. Okay, we try to avoid either one of these two extreme possibilities. So we sort of tend to clamp the velocity to an upper bound sometimes, right? But these are some of the practical considerations in running a particle swarm optimization purely for the optimization type of problems. And the pseudocode, if you go to this particular website, I mean, I have already shared my slides with IEEE Computer Society Bangalore chapter, and you can try these codes on your own, right? Okay, so there are some parameters that we need to tune. And the question is, how many particles should I consider in my swarm? So purely based on empirical evidence, people have used typically between 20 to 50 particles. Okay. The question could be, what will happen if I increase the number of particles in my swarm? Well, it becomes computationally expensive because, as I said, each particle has a memory. So there is a direct impact on your machine memory. Okay. All right. And then these acceleration coefficients C1 and C2. What do I do? Okay, with these two. And then what is the maximum limit on the velocity that I should impose? So it turns out, once again, purely from empirical observations, that the sum of C1 and C2 is kept at 4. 4. Okay, the number 4. Okay, so here are the questions: how to choose the parameters. But I mean, you would ponder over these questions only if you limit your vision to solving some hard optimization problems in engineering. But if you think of PSO as optimizer not only in the sense of functional optimization that I'm talking about, you could actually do wonders with it without having to worry too much on tuning the parameters. Okay, all right. Okay. So I think I said this already, right? I mean, the parameter settings purely for an optimization problem. Okay. And these are some of the nasty functions that are being tested for optimization algorithms. So these are known as the benchmark functions. Okay. And you can see why. You can see why. I mean, these are like multiple peaks, multiple lows, right? You could have multiple minimas or multiple maximas. Okay, so if you look at the restrigen function here, I mean, you could see that there is these functions which typically have a value and more than one value, right? So imagine you have dropped a ball from the top of a hill, right? And it gets stuck in the valley. You don't want that ball or that particle to be stuck there, right? Okay. Okay. All right. So therefore, what do? You need to use something else. You probably need to use another additional momentum term to push when a particle is stuck in a valley. You just push it further, right? But if you push it too much, what would happen is it would completely shoot over and get outside, fall outside your search space completely. Then you have to bring that particle back. So these are some of the computational headaches that we have to deal with. Okay, so therefore, I mean, so I just wanted to show you this, right? And some of the standard results that, but luckily, even though these are nasty functions, their analytical optima values are known. So when we test a typical particle swarm algorithm on how good it is to actually be able to reach the optima for these kind of functions, we see that in some cases it does pretty well. Like for example, in the first case, the green back function. What is the green back function? The leftmost function. In this case, the global optima is 0, and we sort of converge at 0.003. But for restrigen and the other function Rosenbrock, and these are really nasty functions, you can see that you are not able to reach to the optimum with the standard PSO. Okay? All right. Well, and there are some other considerations. And whenever that happens, what do you do? Okay. So, well, I mean, I could do everything that I could have, right? But then also such a thing is happening, then it's better I probably kill myself. So typically what happens is that particular particle or some particles are destroyed, right? Or, I'm trying my best, right? And there has not been enough improvement. So what I can do is I can induct a particle. Okay, all right. So this is known as an adaptive swarm size. But these are all hyperparameter, part of the hyperparameter tuning that I'm really not interested to talk about today. But since the slide is, I wanted the slides to be self-contained, I just, wanted to give you some idea. And then you could do something on the adaptive coefficients. And this I already talked about, how to improve your velocity vector by adding an inertia term and so on and so forth. Okay. Okay, here comes the crux. So I had to tell you what a particle swarm optimization is before I move on to what I have done with it. Okay. So far, based on the half an hour discussion that we had, I mean, what I could see is that what you could probably see more importantly is that using this kind of an algorithm, I can optimize a bunch of things. And this is not restricted to, finding the optima for a single objective optimization functions. Particle swarm optimization algorithms are pretty good in solving multi-objective optimization problems, which are, plenty to be found in engineering optimization, like scheduling problems, typically in oil industry, transportation industry, there are multiple objectives to be simultaneously solved at the same time. And all your traditional optimization methods fail horribly. There is no way, right? So meta-heuristic is your only option. Okay, so optimization is one, but that was not my goal. My other complaint with neural networks and deep learning in general is that it is once again, it's some method which is again based on a black box technique, even though it works very well. And there are a bunch of hyperparameters to consider and tune. So can we use particle swarm optimization to do something to improve the performance of a neural network based classification problem. Okay, all right. So in a neural network, the principal thing is gradient descent. Why do we do gradient descent? Because if it's a class prediction problem, you have some activation unit. So in a neural network, you have a forward layer, right? I mean, you have an input layer where you have the data, right? You squeeze the data, process it, store it in neurons in the input layer. And then there is an output layer where you actually output your final prediction value. Okay, remember, since it's a classification problem, you already know your true value. So the moment you produce a final output value, you can quickly compute the difference between the true value and the predicted value and see that whether these two matches. If it matches in one shot, which is usually not the case, then you are happy. You have done a fantastic prediction in one shot, right? But usually what happens is that's not the case. So you have to change something, right? So the moment you see there is some error, you have to come back. And this coming back process is known as backpropagation. So what are you propagating back? You are propagating back the errors that you have incurred by your prediction. How do you do that? There is a set of hidden layers with a bunch of neurons between the input layer and the output layer that we construct, right? So what we do is we propagate the error from the output layer to the hidden layer, and from the hidden layer back to the input layer, update the weights, and this is a fully connected neural network, which means between every neuron of an input layer is connected to every neuron of a hidden layer. If you are using just one hidden layer, which I always prefer to do, right, then it's just one hidden layer. But it's more than one hidden layer, then what happens is the neurons in the first hidden layer are fully connected to all the neurons in the second hidden layer, right, and so on and so forth. And then the neurons in the last layer of the hidden layer are fully connected to every neuron in the output layer. If it's a two-class classification problem, you keep two neurons in the output layer, each storing the class level of that of the data, right? If it's a multi-class classification problem, the number of nodes that you fix in the output layer depends on the number of classes you have in your problem, right? Okay. However, the headache in this neural network and backpropagation is because it's a fully connected neural network, typically, then there are a really large number of weights. And when there are a large number of weights, there needs to be a large number of weight updates. Okay. When you train to do a large number of weight updates during the backpropagation, because why do you need to update the weights? Very, very likely you are incurring error because you have chosen a wrong weight combination of the neurons in the input layer, right? So you need to update those weights. When you update these weights, the corresponding weights updates, because these are forward propagated, right? The corresponding weights update will also change. So if it's a really large neural network, in fact, in our case, when we actually applied particles, yes.
Sorry to interrupt, Snehanshu. I think the slide hasn't changed since last.
I know that. No, I am not changing slides.
Okay. Sorry.
I'm not changing. I'm not changing slides. Okay. Just let me know how much time I am left with. Okay. All right. I think 15 minutes, is it?
Yeah. I think another 10 minutes we have. But yeah, we can have 15 minutes.
15 minutes.
I mean, I'll just need 15 minutes. Okay, so guys, if you are confused why these slides are not changing, the slides are not changing because I'm not changing the slides. Okay, all right, so don't worry. I'm just giving you the big picture here. Okay, because this was the biggest problem that I was stuck for quite some time. Okay, so yes, so what I was talking about in our case, when we actually applied particle swarm optimization in a neural network during the backpropagation, and in a really deep neural network, ResNet 50, which is 50 hidden layers, right? A total 11 lakh, approximately 11 lakh weight updates had to be done. So you can imagine the scale of the operation. And so along with this dilemma of particle swarm optimization and the dilemma of neural network, I had another dilemma that I really don't want to use GPUs to run these experiments. I would still like to do this on my laptop. So what can I do? So how can particle swarm optimization help us? Okay, so these are the questions. Also, there are some other questions as well. So if you really are seeking some inspiration for making some changes in an existing method, here is one form from our side. is that the source of inspiration is to understand and improve optimization techniques in general. That is fine. But I'm not talking about general improvement of optimization techniques, right? In fact, in this particular talk, in the very end, there are a few slides where I have shown how the improved PSO method helps solve the traveling salesman problem, right? But I'm not going to talk about that, okay? But in general, what happens is, I mean, we postulate that swarms behave similar to classical and quantum particles, okay? In fact, the analogy is so striking that one may tend to think that the social and individual intelligence per se in the PSO are after all nice, useful perspectives, okay? And there is a neat underlying dynamical system at play. And this dynamical systems perspective was indeed also useful in unifying two almost parallel streams, names optimization and Markov chain Monte Carlo sampling in general, okay? All right. So in fact, there are papers where people have shown that a stochastic gradient descent optimization technique can be turned into a sampling technique by just adding some noise, okay, governed by Landrivian dynamics. Recently, in fact, a colleague has shown that the connection-based dynamical system is governed by stochastic differential equations, and therefore you can solve those by using neural networks. So while some of these results are new, the connections between a derivative-free optimization, which is exactly my goal is, the derivative-free optimization, and particle swarm optimization is something that we propose here. So the question that I ask is that, is there a much larger, grander template of which all these approaches that I just mentioned are just special cases? What is missing in the puzzle, grander puzzle? Where do meta-heuristic algorithms fit? So these particular questions seem to be useful in two ways. One, can we use the ideas developed in improving stochastic gradient descent and apply them to particle swarm optimization, and vice versa? And can we use particle swarm history and their location awareness to offer derivative-free approximation? Okay, so this is the big thing. So what is a derivative-free approximation? I was just mentioning gradient descent, right? What is a gradient? A gradient is a derivative, right? I mean, if you think of a single variable function, it's just a derivative. Now, in gradient descent optimizers, there are a bunch of loss functions that are used. Okay, some of these loss functions are differentiable, some of these loss functions are non-differentiable. The trouble is, people tend to use these differentiable loss functions because these are nice. Like, for example, a mean square error. If you are familiar with the regression model, you know what I'm talking about. It's a squared function, differentiable everywhere, right? Like cross entropy, a differentiable function. But then there are non-differentiable functions which are much more insightful and intuitive. Like, for example, a mean absolute error. It's a mean absolute error. It's an absolute valued function, the difference between your actual value and the predicted value. But the trouble with this particular function is that you cannot differentiate it. Okay, I mean, there is a point of singularity. So you have to be really smart. I mean, you have to divide the function into a bunch of different spaces, right? Okay. But this particular loss function is more intuitive. Okay. All right. So what typically happens is people tend to not use these loss functions, even though they are more intuitive. I'll give you an example. Let's say your mean square error is your absolute error is 0.9. Okay. But when you square it, which is what you do, and then you present your mean square error, right? The square of 0.9 is 0.81. Which one is better? So even though your mean absolute error is 0.9, the moment you are using mean square error as a metric, you are actually making it look better, right? So the trouble in gradient-based optimization technique is that you have to have functions which are differentiable. Okay. However, we argue that by proposing an improved version of this PSO, we argue that we have successfully been able to approximate the gradient without actually computing. So we use the iterative power of a particle swarm optimization to actually approximate the derivative of a function, and therefore not use the derivative at all in the gradient descent of the neural network in backpropagation when we are training a deep learning model. Okay, all right. How do we do that is what is the question. Okay, so before that, quickly, I will just present the improvement to the existing particle swarm optimization that we propose. So what we do is we add a momentum term. Okay, so our velocity update has a momentum term, and then we update the momentum of a particle, because momentum is something that comes from the neural network motivation. As I said, in that valley problem, right, when a particle is stuck in a valley, you actually give that guy a particular momentum, right, so that it doesn't get stuck there and it goes up again, right? The momentum update is actually a convex combination between the previous momentum and the velocity, and therefore our proposed momentum particle optimization, as a matter of fact, becomes an exponentially averaged momentum particle. Okay, and why exponentially averaged? So in a particle swarm optimization, as I said, there are two components, right? One is the exploration component and the other one is the exploitation. Okay, so typically what happens in a standard PSO approach, the negligible weights applied in the momentum of the PSO do not help much in improving the acceleration required, right? So you actually need to choose some candidate velocity updates for assigning greater weights to those and assign lesser weights to some of the velocity updates which are actually not close to your recent iterations. So let's say I'm talking about a time step t+1, then I would actually give more weights to the velocity at time t -1, t-2, so on and so forth, give more weights to those and give less weights to velocities which are way in the past. Because every particle has a memory, right? Okay, and the memory is always, it's an n-tuple. So if you look at this particular momentum update, I mean, and you do some basic algebra, I mean, which is there in the main paper, which I'm going to share, you will see this very, very clearly. See, beta is a convex combination, right? Which means the value of beta is between 0 and 1. So which means what? If you raise beta to a larger power, that value will be smaller and smaller and smaller. Okay. So if you look at the first term on the right in the momentum, you will see that it is MIT minus n. And the only term on the left is mi to the power t, right? So this is the first term on the right is not the most recent step. So it is not one step before the most recent update. It is actually n steps before the most recent update. So these are some of the velocities and momentums that we should not actually really assign much credits to, right? So therefore, it is multiplied by beta to the power n. Don't think that these numbers came from heaven. These numbers are actually obtained if you do the iterations, even if you open this momentum relation, right? And look at the last term of this equation, right? It is 1 minus beta only. It is 1 minus beta times vi to the power t minus 1. Now, what is the relationship between a t minus 1 iterate and a t iterate? It is just the previous step, right? So what happens is when you are updating, you are giving more weights to iterates which are closer to your present iteration, okay? And give less weights to iterates which are far, far away from the present iteration, okay? All right. Okay. All right. So now, with this idea, what we have done is we propose an equivalence between gradient descent and particle swarm optimization. What I typically, and in the process, we actually have proved a bunch of theorems. And the first theorem is this. The first theorem is this, that the derivative in your gradient descent with respect to your weight update can be represented precisely in using the parameters of the particle swarm. Remember your parameters of your particle swarm, C1, R1, C2, R2, right? And then the nu in the denominator is just the learning rate in your gradient descent, okay? And this learning rate in your gradient descent, these don't be confused with this W. This W is not the weight update of a neural network. This W is the inertia coefficient that you have seen in your particle swarm optimization, okay? So what is typically happening is the derivative, instead of computing the derivative analytically or otherwise, you are approximating the derivative by actually using the parameters of the swarm. I don't think I have the time to go through the proofs in detail, right? But I'll just tell you this, that this is simply done by using Taylor series expansion, okay? And using the ideas of the gradient descent. So what I can show you is a simple Taylor series expansion. I will just show you the last result. So in this particular slide, you look at the result. We are not only able to approximate the first order derivative with respect to the weight update in the gradient descent, we are also able to approximate the second order derivative. Okay, so we know whether a minima is really a minima and not an inflection point, and we also know whether a maxima is really a maxima, not an inflection point. So what happens with this is that the moment we are able to come up with a relationship like this, in the gradient descent, we are not required to compute the derivative at all. We just use this relationship. So this is only the first step in a gradient descent. We have also proved equivalence between stochastic gradient descent and the parameters of our particle swarm optimization, which are the next two slides. I don't have the time, but once again, I'll show you that we do have a bunch of equivalence relations that come out of this. Okay, all right. And this is one example where I wanted to show you how good our approximation is. In fact, there is an analytical result that we also proved, which shows that our approximation to the gradient is of the order of h square. Now, where h is this time step, which means if your time step is low, if you take the time step as t is equal to 0.1, your error will be of the order of 0.1 raised to the power 2, which is 0.01, right? Which is really, really good. And if you look at this, we have taken some test functions just to show before we actually went one leap ahead and applied it to neural networks. We wanted to apply it in certain test functions, and the solid line is the analytical derivative, and the dotted line is the approximate gradient computed by using the particle swarm iterates. Right? We can see where it is minimizing, wherever it is minimizing, it's converging. It may not be very fast, but it's quite accurate. Okay. All right. Now, since once we are sure that our methods are working from a theoretical perspective, we then go ahead and apply it to a layered neural network by using a traditional mean square error loss function. However, let me tell you that this is also applied on other loss functions as well. And we actually have a result in a neural network that the error gradient in a neural network across layers for the ith particle can be approximated by using this. Okay, and the partial derivative that you see on the right is nothing but the value of the gradient with respect to the activation function, and that is not a problem. That is never a problem. Okay, computing that gradient is never a problem. However, if we want, we can approximate that using the PSO parameters as well. Okay, I don't think I have a lot of time, so somebody is requesting. I think probably I have like a couple of minutes left.
Yeah. Another 5 minutes is okay, Snehanshu.
Okay, fine. Okay, so this is just one other thing that I wanted to mention is that when there are multidimensional data sets, right? The traditional PSO and the improved version of PSO, the learning is really, really slow. So in order to accelerate the learning, what we had to do, we had to project those random numbers, those C1s and C2, as a column vector rather than just a scalar. So we use some matrix projections, okay, and use some rotation, right? And we use this particular rotation matrix, and so that it could actually move in multiple dimensions and find the search space more efficient. Okay, what happened was with this, our classification accuracy as well as our approximation accuracy in objective functions has also improved drastically. Okay, all right. So I don't have the time to talk about the implementation details, but in the slide I contain the code link, and there is a README file and a well written documentation of how to use our code, right? And somebody was trying to see. Well, there are a bunch of other things, and this is the order of accuracy. I'll just now go straight to some of these optimization functions and show you that our methods are the best. I mean, at least on the bunch of functions that and these are all benchmark functions. This is purely from an optimization point of view. However, right, I don't have the time to talk about multidimensional optimization and Pareto fronts, so I'll skip these slides, right? So I can see. And the other thing that I wanted to show you is that if you compare some of these test functions, if you compare the gradient descent and stochastic gradient descent, in terms of accuracy also we are closer to the analytical optima, and in terms of number of iterations that we are taking to converge to that optima also way faster than some of the present methods. In fact, we have compared it with all the benchmarks. Okay. Now, what we have done is, as I said, because the idea was to use this improved version of swarm optimization and classification problems, we had to take a bunch of benchmark data sets. Some of these are binary classification data sets, some of these are multi-class classification data sets, and we actually compared our results with the state of the art. So in order to do that, we used two architectures. So one architecture is just a shallow neural network, input layer, hidden layer, and output layer, right? Okay. And the other one is a convolutional neural network on which we have applied some computer vision datasets like MNest, FashionMNest, Cypher 10, and Cypher 100. Okay. So in this particular datasets, if you look carefully, in terms of loss and accuracy, we have beaten Adam on many times, and on a few occasions we are as good as Adam. Adam is actually a state-of-the-art optimizer, as you might know. And there are some of other state-of-the-art optimizers like AdaGrad, AdaDelta, DeepGrad, and things like that. We have compared our results with those as well. Okay, so these are data sets that are taken from UCI. I have also used it in some of our other data sets as well, some astronomy data sets, but I did not include those results here. Okay. And if you go to this computer vision data sets, you can see, except for Cypher 100, for the other three data sets, the accuracy-wise, loss-wise, and execution time-wise, we are actually better. Okay. Just to give an example, in FashionMNest, we converge in 900 seconds, while Adam converges in 990. Our test accuracy is 99.48%, where Adam's test accuracy is 99.32. Okay, our best loss is 0.017 and Adams is 0.027. Okay, so I mean, this was expected. This was expected because the approximation order is very good. When we have approximated gradients very well, and since we did not have to compute gradients, which is usually an Hessian computation, and therefore time taken, I mean, we save some time. This is despite the fact that PSO is an iterative algorithm and it has its own disadvantages in terms of execution. Okay, and these slides are multi-objective optimization. I don't have the time, but nonetheless, I have already shared the slides with the IEEE guys, and they would be happy to share the slides. I will just go to. So in conclusion, I would say that the first thing that we did was that we improved the present PSO optimization algorithm and gotten improved results on a lot of engineering optimization problems, which is single objective and multi-objective. We have then proved a bunch of equivalence theorems between derivatives and gradients, and eventually ported our method to backpropagation, gradient descent in backpropagation, and replicated most of the neural network classification results using this. We have also proposed a rotational variant of our PSO algorithm to handle high-dimensional data, right? Okay. There are a few things left, which is, I mean, I really don't know theoretically how fast this method is. I mean, what is the order of convergence, the speed of convergence, and things like that. Typically, in computational approximation algorithms, there is always a trade-off between accuracy and speed. So we haven't really studied that trade-off, but that is something that we are actively pursuing now. So there is some standard literature that you could actually go through. I have included in the slides. And if you want to read my paper, a general tutorial paper as well as this particular paper on which this talk is based, and there are a bunch of codes that are available as well. Okay, so all right. Yeah. So what is my reckoning at the end of the talk? I would say that I tend to believe in this kind of algorithms more than I used to a couple of years back. Okay, so I'm open to questions now.
Yeah. So shall I move to questions?
Yeah. I'll just 1 second. Something happened, and I cannot go to. Oh, I'm kicked out of the meeting somehow.
Actually, you are still in the meeting. I'll quickly.
Okay. All right. So I'll just go to the chat.
Yeah. So shall I read it out or?
No. I can see. I can see. So when you do not.
Before we start answering questions, participants, if you have any questions, kindly post them in the chat window. It will be easier for us to track them and answer the questions.
Okay, so I have questions. See, can there be a hierarchical organization of swarms? I'll read out the questions for the benefit of all the audience. So can there be a hierarchical organization of swarms, that is swarm of swarms, to keep the communication overhead low? Yes, there can be. But once again, if you have, so you are talking about more than one swarm, right? Yes. So actually, in the context of transfer learning, when you do transfer learning in deep neural network, that is also sort of, in the context of transfer learning, this can be efficiently used. I haven't really thought out the details of it. The communication overhead, if you have one swarm, the communication overhead is usually not much, as long as you have, tuned your hyperparameters, and you don't have to change the tuned parameters over and over again. Generally speaking, more than one swarm is computationally intensive, but it could be done in a hierarchical way. Yes. Okay. So request you to present some case studies and comparison of results with PSO and other optimization methods. I have exactly done that in the table that I have shown, right? Okay. I think the results are very, very encouraging. Okay. I mean, beating Adam, which is a state of the art, is no easy task. I mean, people use Adam left and right. Okay. So yeah, different weights will have different mass. So what is the concept of mass in the momentum? Does different weights will have different mass? Yes, that's the case. Beta mi plus 1 minus beta vi dimension mismatch. No, the betas are actually vectors. All right, so there is no dimension mismatch. So so these are the 4 questions. Let me scroll down here on the slide of order of this. Okay, now okay, all right. So how about considering PSO for mixed irregular and regular search spaces? Well, I mean, many of these search spaces that I have used in the optimization problems, I mean, see, I mean, it's 1 hour talk, cannot be on optimization and neural network-based classification. So the geometry of the search space so far hasn't mattered. Okay, so I have sort of, but there could be some other considerations like topological folding and such. Okay, so that we haven't really thought about, but it's a good thought nonetheless. Okay, I will keep that in mind. Yeah.
Yeah. Does anyone have any questions?
So these are like 5 questions that I could see in the chat box, and I answered. Right. I mean,
Yeah, 5 questions were there.
Yeah, you have to run the code and see for yourself, and there are 5 proofs in total before we establish the gradient equivalence. So you need to understand those proofs also. Okay.
So we have another question.
Yes. Yeah. Okay. The global best is always better than the personal best, but you cannot jump from your initial position to a personal best, right? Okay. So we are moving from the direction of personal best to a global best. Because what happens is there is a local search in a PSO. So you compare your personal best among some friends locally. See, one particle in a swarm is not expected to talk to every other swarm in that candidate solution space. That becomes computationally expensive, right? So it talks to its neighbors, a very small set of neighbors, right? And then updates its personal best, and then compares if that personal best is better or worse than the global best. So you need personal best. We can.
Do we have any questions?
Yeah, there is another question. The initial location of the swarm particle is arbitrary. Yes. Can we spawn multiple swarms at different locations? You mean, see, there are multiple swarms. I mean, when you talk about swarm is a collection of particles, Sudhika. Are you talking about particles or swarm? Are you saying can we spawn multiple particles at different locations as well? I mean, If you're talking about multiple particles, I have answered your question already, right? Yes, there are anyway particles are geometrically distributed in the search space, right? So I don't understand the. I think you mean particles. Okay, I don't think I mean.
Participants, kindly post your questions to everyone so that people can see it.
Yeah, because this particular question is actually posted privately. So what I'll do is I'll copy and paste. Yes. Okay, so that everyone can see. And I have already answered that question.
Kindly post your questions to everyone. Do we have any more questions? Kindly post them in the chat window.
Yeah, it seems 1 hour is never enough. I actually wanted to talk a bit more about the equivalence, but I didn't.
We have another question.
What is a typical use case where we have multiple swarms? How will the behavior vary? I don't have answer to that yet, because as I said, I haven't really worked on or thought about multiple swarms, because I did not need multiple swarms to solve any of the problems that I discussed. And we did actually solve um, a lot of problems. We solved the particle traveling salesman problem. We solved the 0-1 knapsack problem. We solved single objective constraint and unconstrained optimization problems. We solved multi-objective constraint and unconstrained optimization problems. And then we solved this neural network-based classification. So we did solve a lot of problems. I would say in traveling salesman problem, in order to scale up the solution, this may help, but I mean, in terms of behavior, the individual update equations will not change. What changes is how you are communicating from one swarm to another. So there needs to be some table to keep communication head, because typically the reason why you use more than one swarm is that suppose you have in one particular swarm the global best is actually doing much better than the global best of another swarm. So what you do is eventually you either kill that swarm or you migrate that particle to another swarm. That's what you do, right? So the particle dynamics will not change much.
So, do we have any more questions?
So I'm also available on LinkedIn. You can send me messages. I'm available over email. How do we ensure that memory is updated like evaporation to prevent see, each particle has a memory, right? Actually, if you have seen the update, right? I mean, if you've seen the momentum and the velocity update in the improved version of my swarm, you have seen that I have kept all previous velocity locations. Okay. In a typical PSO, what happens is only the present iterate and its immediate past iterate is kept. But if you look at the momentum update equation, which is, if I remember correctly, MIT equal to beta MIT minus 1 plus 1 minus beta VIT. Each one of these terms is actually a nested term of all previous velocities and momentums. Okay. So, and the trade-off is actually we give lesser weights or greater weights to more recent velocity or momentum updates and lesser weights to the past momentum updates. So I don't think its evaporation is an issue here.
If anyone have any questions, kindly post them in the chat window.
Yeah, you can also ask questions in sending me a message, LinkedIn, or reaching out to me. These days, everybody's footprint is available online.
Correct. So actually, I have some question for you. This is not technical at all. So this is kind of quick questions that you have to think less and answer fast.
Yeah. Anand, you're breaking up. Can you repeat?
Yeah. Am I audible now?
Yeah.
Yeah. So I have some quick questions for you. These are like think less and answer fast kind of questions. So the first question I have is like for most people, maths is kind of very tough subject. So what do you think about that? Any comments?
Well, I mean, see, there are two ways of approaching any applied problem. One is you are pretty good at solving the problem without caring for the math at all, right? And but if you do that, your approach will be a black box approach. You understand the parameter tuning, you understand the overall dynamics, you understand the method quite well, but you really don't understand or care much about the math. That is okay. So then your focus should be purely on applied AI. Like for example, I had one question, right? I think that particular audience actually did not care about the math. So I mean, he or she was asking me, what are the use cases, what are the applications, right? I mean, it's nothing offensive, but I mean, if you really think about it on the flip side, let's say I don't put any applications at all, nothing, right? And I write a paper and I submit to a journal, I'm pretty sure it will be accepted for the sheer value of it. So math gives you the value and the perspective. So if you are not good at math, that's okay. But I mean, at least you need to try to understand the implications of math. Okay, because the results that we got is not black magic. The results that we got is because we have been able to come up with a theoretically sound approximation to error gradient in the neural network. Okay, right? So math will help you see beyond the meta heuristic. And there are ways to improve your math skills. I mean, there are so many good courses online. But one thing that I always tell my students is that whenever you learn a method, actually, Anand, what happens in India is the way math is taught in schools and colleges and in universities is actually awful. It's really awful. I mean, that's not the way to teach math. We are taught, like when I was in school, I remember, we were taught to remember formulas. We are taught to apply those formulas in set problems. Okay. Even in high school, we were encouraged to do long integrations. We were never told why I should integrate a function over a space. So the insight itself, so what happens is the tricks and techniques become more important than the insight. Math is not about tricks and techniques. It is more about the insight. Okay, so for those who are not good at maths, my only suggestion would be try to get better, because without that, it will be difficult to do anything new. You can perfectly do well in your jobs, right? Probably solve some applied problems, right? But in order to do something, in order to contribute something new, may not be possible.
Every time we have talked, like you have always brought up astroinformatics. Why astroinformatics, and how did you reach there?
Oh, that was actually, I think I was giving a talk in Maulana Azad National Urdu University in Hyderabad. It was in end of 2014 or beginning of 2015, I don't remember. Okay. And there was one famous guy, really famous. He's the director of the Inter-University Center for Astronomy and Astrophysics in Pune. So he was actually giving a talk on minimum spanning trees. An astrophysicist giving a talk on minimum spanning trees. He was trying to explain how he used minimum spanning trees in his search for hidden galaxies. Okay. And then I thought, when he was talking about this minimum spanning tree, the way he was describing the search procedure, I immediately asked him a question: can we use some kind of a meta-heuristic search technique instead of using MST? And then he immediately said, yes, why don't we talk about it? Then during lunch, we sat down and we talked. And then I started talking to him about this. And then he said, okay, fine, why don't you come to Ayuka, where he was? And then I said, I don't know anything about astronomy. So then he gave me a data set. He gave me a data set on exoplanets, which are like planets outside the solar system. And then he said, let's see whether we can come up with a search method for an undetectable exoplanet. Can we do it? And then I spent some time, and the way we did it was basically a swarm-based search technique. Okay. And we kind of solved the problem. And then I went back to him. I was still not very confident, and this was May 2015. I think I went back to him. I showed him the solution, and then he said he saw some merit in it, and then he said, "Okay, fine. Why don't you consider using some machine learning methods in astronomy?" But then I was not interested. I am never interested in applying one particular method to a data set. So then different sort of data sets like stars, galaxies, quasars, finding double peaks. In fact, there is a very interesting problem that I was working on, and that actually led me to exploring particle swarm further. Is that if there are multiple peaks within a galaxy, how do you detect it? Because the image is just a 28 by 28 image, pixel image, right? So to answer your question, I mean, people have been kind, and then there are astronomy community, very strong astronomy community in Bangalore, as you might know, right? I mean, those guys started talking to me, and they gave me problems and data, and so in order, and most of those problems are sort of unique problems. So in order to solve those problems, we came up with methods. So that's how I got interested, and now I am still, but I don't consider myself an astronomer. I mean, some people refer me as an astronomy guide, and I'm like, I'm very, very flattered to hear this, but I'm not an astronomy guy. I mean, in fact, you are insulting the real astronomy guys by referring to me as an astronomy guy. What I do is I try to, solve some machine learning based problems in astronomy. And
Awesome. Yeah, thanks a lot. Another question is, do you like Dr. Saha during the lockdown or Dr. Saha before the lockdown?
I don't like Dr. Saha at all. I mean, I prefer people calling me by my first name.
Okay.
I mean, you might have noticed during when we worked together, I never used to write Dr. Saha. So, I mean, I just write my first name.
Sure. No, I'm asking like, is it lockdown or before lockdown? Which is your favorite part?
Favorite part of what?
Life? Because now everyone is in lockdown. So,
Oh, okay. I think it hardly makes any difference to my life because I barely step out of my academic boundaries. I mean, I think I came to Goa on December 31st. I think. Okay, on the New Year night, New Year Eve, and between that time and the time that lockdown started, I could tell you that there are only a couple of places in Goa that I have visited, and none of those places are actually a beach, sea beach. So I mean, it makes no difference to me actually.
okay.
I understand that a lot of people face depression and all, and I mean, but I do some physical activity inside home and go to my terrace, but generally it doesn't depress me. I mean, if I have to be stuck in a room or in my house, it's okay. I think I'm fine.
Yeah, awesome. So,
Okay.
do you watch movies often or
Yes. I do
okay, which
watch
is your
movies.
favorite movie which features a lot of AI ML stuff?
And I mean, most of those movies are crackpots, Anand. See, a lot of AI ML stuff that they show in the movies are just crackpot stuff. I mean, those are not the things that actually happen in real life. I mean, I don't think. In fact, some of the real humor around AI and ML is the real stuff. Because yesterday I saw somebody's tweet. I mean, he was actually castigating Indigo for transporting him to Calcutta and sending his luggage to Hyderabad, right? But
Yeah.
since he used great job sarcastically, the bot in Indigo thought that they really did a great job, and the reply was, "We are really glad to hear that." So somebody is telling you that you did a great job by transporting me to Calcutta and sending my luggage to Hyderabad, and you reply, "I'm glad to hear that." So
Yeah.
so that's really one of the things that ticked me off. I mean, these kind of mistakes happen all the time. Okay. So,
Right.
I mean, AI and ML is not a magic wand. We are able to solve some problems more efficiently. We are not able to solve a lot of problems, actually. We should actually accept the limitations.
Sure. Yeah, that's all I had. Thanks a lot for answering those questions. If
Thank
anyone
you.
have any questions, kindly post them in the chat window. We are about to close the session. Dr. Saha, any closing remarks?
No, I think I felt good giving the talk. I mean, I wish I could go on and then have another hour or so, but maybe some other time. But I mean, I also like the kind of questions that were asked. I mean, it's sort of indicates that you were attentive and you wanted to get something out of it, and that is really heartening.
And yeah, thank you, Snehanshu, for a great webinar. And also to all the participants for taking time out of a Friday morning and attending this session and asking great questions. And you can always write to Snehanshu via his LinkedIn
Yes, definitely.
profile, or also through IEEE Computer Society social media channels, either Twitter, LinkedIn, or Instagram. So if there is any other question, yeah,
Yeah,
or
I
not,
think Vishwa, somebody is asking for a feedback form. I think probably due to logistic problems, I don't know whether we'll have feedback forms, but you are encouraged to write whatever you want on that LinkedIn page, right? I mean,
we do have a feedback form for each
okay.
session.
Oh, I see.
So yeah.
Yes.
Along with the slide deck, uh,
Hmm.
we will share the feedback form, and we'll quickly pass the feedback back to you if they're relevant to the technical content of the talk.
Yeah. Those who are, I mean, I would say those who are really interested, please read my paper. It's on slide number 81 or something. I don't exactly remember, but the full paper is there for free, so you can download it and read it.
ResearchGate, I think you've already provided the
Yeah.
PDF versions.
Right.
Yeah, participants
I
are
can also send the PDF. I can also send the PDF if somebody is interested. I don't want to broadcast it, right? But if somebody is interested, I can just send the PDF as well.
absolutely. I mean, this is a forum for further collaboration if somebody is really interested and working on similar lines.
Right.
We always encourage this kind of a collaboration. Thank you, Snehanshu.
Thank you,
And
Vishwas. Thank you, Anand, for inviting me. Thanks a lot.
it was a pleasure hosting you. And thank you, Anand, for being a great host again. And we will have more webinars coming in the next few weeks. We'll keep you posted. Please do follow us and stay safe. See you next time. Thank you.